Hey guys, we are going to be starting out with our thermochemistry unit. This is going to include gas laws, different states of matter, and how heat changes throughout the course of a reaction. Today we're going to focus on some of our basic gas laws, including our combined gas law. And we're going to be looking at doing some calculations with these. First off, look at properties of gases, of how we're actually measuring stuff, what type of variables we look for with gases. Remember, gas particles, they're moving very quickly. There's a lot of empty space between the particles. So gases are easily compressed because there's a lot of empty space between the actual particles. Compressibility is the measure of how much the volume of matter decreases under pressure. Um, and temperature, volume, and the amount of gas you have all affect that gas pressure. So we're mostly going to be looking at pressure, but also variables that are going to affect pressure. So the variables we're going to be dealing with, pressure is our P. You may see it measured in kilopascals or kPa. Other pressure units that you have are on your reference sheet on the front. You also have atmospheres or ATMs. There's also torr, which is TORR, and millimeters of mercury, which is mmHg. The most common ones you're going to see are the kPa and the atmospheres, the ATM. Volume is measured in liters. That should be a capital L. So whenever you're given volume, especially if there's only one volume variable and not two, you need to make sure to change to liters. We're dealing with temperature, which is in kelvins for all of our gas laws. So remember back in Unit 1, we converted between degrees Celsius and Kelvin by adding 273 to whatever the temperature is in Celsius. And that formula is given on your reference sheet. And then tomorrow, we're also going to talk about gases in terms of moles, or how much is in a system. So looking at how these variables affect gas pressure. And a lot of this you already know, maybe just not in scientific terms. But if you add more gas to an enclosed rigid container, the pressure will increase if the volume stays constant and the temperature doesn't change. So think of if you're driving and your tire pressure is low. You can't actually change the size of the tire or the temperature of the tire, but you might stop at a gas station, put more air in the tire. Simply because the more particles there are, the more collisions between the particles, which is what creates that pressure. If you reduce the volume of a container a gas is in, it's in a smaller place, so the particles are closer together, they're going to collide more often, increase the pressure. If you increase the temperature of a gas, remember if you increase the temperature, the particles are moving faster, so they're going to collide more often and the pressure is going to increase. So that's looking at how the other variables change pressure. And when looking at what happens to pressure, you're always looking at, are there more collisions between particles or less collisions between particles? So let's look at our first gas law we're going to deal with. Today we're going to look at 3 individual gas laws and then look at the combined gas law that includes all 3 of them. So with Boyle's law, which is looking at how pressure and volume are related, if the temperature is constant, as the pressure of a gas increases, volume decreases. And same thing, if pressure decreases, volume will increase. So Boyle's actual law states that for any given mass of a gas at a constant temperature, the volume of the gas varies inversely with pressure. So remember, inverse means they go in the opposite direction. So if one goes up, the other goes down. If one goes down, the other goes up. The individual formula for Boyle's law, only comparing pressure and volume, it's the beginning pressure and volume is going to be equal to the final pressure and volume, whenever they're multiplied. So we're going to look at a couple problems just using Boyle's law. So I'm going to write Boyle's law up at the top as we're going through the examples. So this was P1 V1 equals P2 times V2. So here we have an example of a balloon that has 30 liters of helium gas at 103 kPa. What's the volume of the helium when the balloon rises to an altitude where pressure is only 25 kPa? The hardest part with these is figuring out which particles are going to, which variables go on which side together. So always look at different measurements that are paired together. So we have a balloon that's 30 liters at 103 kPa, so those need to go on the same side together. So our initial pressure is 103 kPa. Our volume is 30 liters. And it tells us that our pressure is going to drop to 25 kPa, and it wants to know our new volume. And you can kind of guess what happens since we said that they're inverse. So pressure is going to go down, so our volume should go up. And we're simply going to do some basic algebra to solve for volume. So we would end up doing 103 times 30, and we're going to divide by 25 to get a final volume of 123.6. And always make sure to put appropriate units on here, so that should be liters. And generally, you're going to be given more sig figs than I gave you. 30 liters, I'd probably have a decimal there where it's 2 sig figs. The 103 kPa has 3, 25 kPa has 2. So we would round our answer to 120 liters with the appropriate number of sig figs. Let's look at another problem using Boyle's law. So still using PV equals PV. So we have a gas with a volume of 4 liters at a pressure of 205 kPa that's allowed to expand to a volume of 12 liters. What's the pressure in the container if the temperature remains constant? So yet again, figure out what needs to be paired together. So we have a gas at a volume of 4 liters and pressure of 205 kPa, so those will go on the same side together. And then that's allowed to expand to a volume of 12 liters, and we're looking for the pressure. So now we need to solve for P. So we're going to do 205 times 4 divided by 12. So our pressure is going to be 68.3. And for 4 liters, we only had 1 sig fig. So we could actually round this to 70, and our unit of pressure was kPa. Going on to our next gas law. Our next law is Charles's law. This one is comparing the relationship between volume and temperature. So as temperature of an enclosed gas increases, volume also tends to increase when pressure is constant. So Charles's law states that the volume of a fixed mass of gas is directly proportional to its Kelvin temperature if pressure is constant. So if they're directly proportional, they are going to move in the same direction. So if one increases, the other increases. If one of them decreases, the other one will decrease. And the formula for Charles's law, it's going to be the initial volume divided by the initial temperature. And remember, temperature, it says, needs to be in Kelvin, is going to be equal to the volume, the final volume over the final temperature. So let's look at how these are going to work out. So I'll write our formula up here. V over T equals V over T. So we have a balloon in a room at 24 degrees Celsius that has a volume of 4 liters. The balloon is then heated to a temperature of 58 degrees Celsius. What's the new volume if the pressure remains constant? So it tells us that we have a balloon at 24 degrees Celsius with a volume of 4 liters, so that will go on one side together. So we have 4 liters over, and our temperature it gave us was 24 degrees Celsius, but remember, temperatures have to be recorded in Kelvin. So remember, to go from Celsius to Kelvin, we have to add 273. So 24 plus 273 is 297. And then we're looking for the new volume when our temperature goes to 58 degrees Celsius. 58 plus 273 is 331. And to solve for volume, you need to get volume by itself. So you would end up doing 4 divided by 297. And then to get volume by itself, you need to multiply by 331 on both sides. And that's going to give us a volume of 4.46 liters. And generally, you're going to be given more numbers for sig figs, but based off of the 4 liters given, there's only one sig fig in that number, so you can round this to 4 liters with that one sig fig. Let's look at another example with Charles's law. So that, remember, was V over T equals V over T. So if a sample of gas occupies 6.8 liters at 325 degrees Celsius, what will its volume be at 25 degrees Celsius if the pressure does not change? So same thing, make sure you figure out what pairs together on the same side. So we have a gas that's 6.8 liters at 325 degrees Celsius, but we need to change to Kelvin. 325 plus 273 is 598 Kelvin. And we're wanting to know what's the volume at 25 degrees Celsius, which 25 plus 273 is 298. So looking for our final volume, we're going to have to do 6.8 divided by 598, multiply by 298 to get volume by itself. And we get that our volume is 3.39 liters. And in terms of sig figs, both the 6.8 and 25 only have 2 sig figs. You can also base your sig figs off of the Kelvin temperature. So technically 25 degrees Celsius, when you change it to Kelvin, will have 3 sig figs. So you can base it off of the 6.8 liters with 2 sig figs and round this to 3.4 liters with the appropriate number of sig figs. Our third gas law is Gay-Lussac's law, which is comparing pressure and temperature. So as temperature increases, pressure is also going to increase because there's more particle collisions. So Gay-Lussac's law states that the pressure of a gas is directly proportional to the Kelvin temperature if volume is constant. So remember, directly proportional means they go in the same direction. If one of them increases, the other increases. If one of them decreases, the other decreases. And the formula for Gay-Lussac's law is your initial pressure divided by your Kelvin temperature is equal to the final pressure divided by the final temperature in Kelvin. So let's look at how these are going to appear. And I'll write our formula up above. We have P over T equals P over T. The gas in a used aerosol can is at a pressure of 103 kPa at 25 degrees Celsius. If the can is thrown into a fire, what will the pressure be when the temperature reaches 938 degrees Celsius? And do you remember that temperatures have to be reported in Kelvin? And understand that it would probably explode before it reaches that temperature, but just for mathematics' sake. So you want to make sure that you pair the correct numbers together. So our can was at a pressure of 103 kPa at 25 degrees Celsius. So our pressure is 103. 25 degrees Celsius changed to Kelvin by adding 273. So that would be 298. We're looking for the new pressure when the temperature is 938 degrees Celsius. So don't forget to change to Kelvin. 938 plus 273 is 1,211 in Kelvin. So to solve for pressure, we're going to do 103 divided by 298 and then multiply by 1,211 to get it off the bottom. And that is going to be a pressure of 418.6. And our pressure unit is in kPa here. In terms of sig figs, there are two possible answers. Normally, you want to base it off of what you wrote in your actual equation. So if you look at both 103 and 298, they both have 3 sig figs. So we can round our answer to 3 sig figs. So it would round to 419 kPa. Let's look at another problem. So our formula, remember, is P over T equals P over T. The pressure in a car tire is 198 kPa at 27 degrees Celsius. After a long drive, the pressure is 225 kPa. What is the temperature of the air in the tire? So our initial pressure and temperature is 198 kPa at 27 degrees Celsius. Oops, excuse me. I'm talking and not paying attention to what I'm writing. We're just going to X that out. So we need to change to Kelvin. So 27 plus 273 is 300 Kelvin. And that's equal to our final pressure, which is 225 kPa. And we're looking for our final volume. These tend to be the trickier ones to solve for because you have to make sure to get volume off the bottom. So in situations like this, I might simply cross multiply to make it easier on myself. So I'd say, okay, we have 198 times volume is equal to, see, 225 times 300 is 67,500. and divide by 198. To get a volume of 340.9, oh, excuse me, a temperature. I don't know why I wrote V. Excuse me, 340.9 Kelvin. And yet again, sig fig wise, everything would be to 3 sig figs, even the 300, because you added to 273, there would still be a decimal at the end. So we could round this to 341 Kelvin as our final answer. All three of these smaller gas laws are not on your reference sheet, but they are in the combined gas law that's given on your reference sheet. So the combined gas law combines Boyles's, Charles's, and Gay-Lussac's law to describe the relationship between pressure, volume, and temperature of an enclosed gas. So the combined gas law is PV over T equals PV over T. So if you'll note, you can see Boyles's gas law was the P times V equals P times V. Charles's was the V over T equals V over T. And Gay-Lussac's is the P over T equals P over T. So you can find all three of those smaller laws within this one law. Let's look at how these problems will be presented. So I'm going to write our formula up top. PV over T equals PV over T. So we have the volume of a gas-filled balloon is 30 liters at 313 Kelvin and 153 kPa of pressure. What would the volume be at standard temperature and pressure? So standard temperature and pressure are constants that are given on your reference sheet. So if you look on the front page of your reference sheet where it says chemistry reference tables, on the left side, the third and fourth thing down are standard pressure, and it gives you standard pressure values in all of the different pressure units. And then you also have standard temperature given in Celsius or Kelvin. So those can be used in multiple situations. I know we used those briefly and talked about them whenever we were doing volume conversions with mole. But still, you're going to have to make sure that you put the appropriate units on, or the appropriate variables on the right side together. So it tells us that the volume is 30 liters at 313 Kelvin and a pressure of 153 kPa. All three of those go on one side together. So our beginning pressure is 153. Our beginning volume is 30 liters. Our beginning temperature, it gave us in Kelvin, so we don't have to convert. That's 313 Kelvin. And then it wants to know the new volume at standard temperature and pressure. So we would have to pick those numbers off of our reference sheet. Since our pressure is in kPa, standard pressure in kPa is 101.3 off of your reference sheet. And standard temperature in Kelvin for gas laws, it gives you is 273. So anytime it mentions the STP or standard temperature and pressure, make sure to look on your reference sheet for those values. And the easiest way to solve these problems, yet again, is to cross multiply. And whenever we solve, you end up having 153 times 30 times 273, which is equal to 125370. The other side, you have 313 times 101.3, which is equal to 31,706.9. When we divide them, we're going to get a volume of 39.5 liters. And I would normally give you more, so I would probably have a period at the end of 30 liters, so we'll do it to 2 sig figs. So we'll round this to 40 liters as our final volume. Let's look at one more example with these. Oh, it kept writing from the previous slide. Okay, I'm just going to X that out because it was from the previous slide and it's not going to let me erase. So using the same formula, the PV over T equals PV over T. We have a 5-liter air sample, has a pressure of 107 kPa at a temperature of 25 degrees Celsius. If the temperature is changed to 102 degrees Celsius and the volume expands to 7 liters, what will the new pressure be? So figure out what variables you're given and make sure to put them on the appropriate side. So the 5 liters, 107 kPa, and the temperature of 250 are all the same sample of air. So our beginning pressure is 107. Beginning volume is 5 liters. Beginning temperature is 250 degrees Celsius, so add to 273. That is 523 Kelvin. Our new pressure is what we're looking for. The volume changes to 7 liters. And our new temperature is 102 degrees Celsius. So add 273. That's 375 Kelvin. Yet again, I would go ahead and cross multiply. So you're going to end up doing 107 times 5 times 375. You're going to end up dividing by 523 times 7. So that's going to give you a pressure of 54.8. And our pressure unit is in kPa. And the volumes, I would normally give you more digits, but both volumes only have 1 sig fig. So we can round this to 1 sig fig by making it 50 kPa. Make sure to practice these whenever you're doing the posted combined gas law practice. You can use this combined gas law to solve all of these gas law problems. But if you're not given a variable, you simply ignore it. So if you're not given any temperatures, ignore temperature, and you're left with Boyle's law, that P times V equals P times V. If you're not given pressures, ignore that unit, and you have P over T equals P over T for Charles's law. If you're not given any volumes, ignore it, and you have P over T equals P over T to make up Giley-Sacks law. But whenever you're doing these, the big thing is make sure do not forget all temperatures need to be in Kelvin.